while learning and learn the smarter way. It's very important that our learning should be connected to the real world so that we can digest what has been taught and it remains in our mind for a longer time and it can be reproduced whenever you need it so that you can apply it and get a satisfaction out of that. This video connects real-life scenario of auto-scaling with auto-scaling in software. You will learn what is the benefit of seeing this. So, the benefit of seeing this video, you will start applying technology and weigh it as how useful it is in terms of reality. Ask us most real use case questions and explore technology. Benchmark. Let's start watching a video which is very useful now in terms of scaling and how does a machine scale by itself due to increased load, how the load should be distributed, how should you do a scaling in real life, what are the necessary factors if that's not lifted properly, what are the dangers of that is very important for understanding. So let's connect to real life scenarios with autoscaling.
On Tuesday the 13th of December 2016, a Virgin Australia Boeing 737-800 aircraft was being prepared to operate Flight 1393 from Adelaide, South Australia to Brisbane, Queensland. At 9:27 Central Standard Time, the graphical load instruction report was sent to the ramp staff allocated to load the aircraft. Virgin Australia used an electronic load control system, which was accessed by the leading hand on a mobile tablet device to organise the loading of the aircraft. The GLIR indicated the Brisbane-bound bags and all cargo, including seafood and 4 dogs, were to be loaded in the forward compartment, and the bags which would be transferred to connecting flights and the priority Brisbane bags were to be loaded in the aft compartment. While loading the aircraft, a member of the loading staff advised the leading hand that the Brisbane bags would not fit into the compartment with the cargo unless they were placed on top of the dog crates. If the bags were placed on the crates, the loading staff thought the dogs may not have had enough oxygen to breathe. To resolve this issue, the leading hand used the LCS to move 55 bags into Section 31 and save the changes in the system. When the changes were made, the Move Mode and Ramp Clear Mode buttons on the tablet screen grayed out and the load control status changed to LL. The loading staff proceeded to load these bags in Section 31. When the leading hand refreshed the device after the bags had been moved, the status returned to normal, and the leading hand presumed the changes had been accepted. At about 9:38, the load controller in Brisbane noticed an approval request in the LCS for the load to be redistributed. This request was for 55 bags, equal to about 870 kilograms, to be moved from Section 21 to Section 31. The LCS will allow the leading hand or load supervisor to move up to 500 kilograms of freight, provided the center of gravity moment does not change by more than 5 index units without the approval of the load controller, only if the resultant center of gravity remains within operational limits. However, as this amount exceeded the limits, the change needed to be approved by the load controller. 2 indications were generated by the LCS for the leading hand, indicating the system was locked and the takeoff index was exceeded. A high priority message was also shown on the load controller's screen, stating the takeoff index had exceeded the aft limit by 4.8 units. This meant the aircraft was no longer within the required center of gravity limits. In response, the LCS was locked for 7 minutes while the load controller calculated the required changes to the load and approved the changes in the LCS. The load controller calculated that moving 40 bags from Section 31 of the aircraft back to Section 21, or moving a number of passengers forward, would be enough to return the aircraft to balance. Because the leading hand was using the mobile application, the load controller thought they had a direct line of communication with the leading hand, so they used the inbuilt messaging system to send a message. The load controller received no response from the leading hand and amended the LCS. The flight information was then unlocked so the ground crew could continue to update the LCS. The leading hand did not receive these messages and they subsequently finalized the flight without making any changes or checking the LCS, and the final documents were released by the LCS automatically. This indicated the changes had been accepted and the aircraft had been loaded correctly. After the aircraft had departed, the leading hand was rechecking the paperwork and saw the bags had been moved in the LCS back to Section 21 by load control. The leading hand then spoke to the airport movement coordinator. The AMCO attempted to contact the aircraft by radio but received no response. The AMCO then contacted the load controller to explain what had happened. The load controller determined the aircraft was out of balance by 4.8 index units past the aft limit for takeoff, and the flight crew should be advised 40 bags, equal to 626 kilograms, were in Section 31, not 21. To return the aircraft to balance, the load controller advised the AMCO that 3 passengers would have to move forward from Zone D to Zone B. When the flight crew rang for the departure call, the AMCO passed on this information. However, when asked to confirm they had received the information, there was no response. Flight dispatch then contacted the flight crew via satellite phone and confirmed the flight crew had received this information. The flight crew contacted the cabin supervisor with the request to move 3 passengers forward. There were no control issues during flight. The first step for users in the LCS is to subscribe and add themselves to the flight. This is undertaken to ensure the messages are received by people within the network, such as AMCOs, load controllers, freighters, and leading hands. This is not a compulsory page in the LCS and can be skipped when opening a particular flight. The leading hand had not subscribed to the system, meaning they did not receive the messages from the load controller about the aircraft being out of trim due to the movement of baggage. When the baggage was initially moved to Section 31 by the leading hand in the LCS, the system locked. This did not provide clear indications that the load distribution change needed acceptance by the load controller before proceeding with loading the aircraft. The leading hand was not sure what the load control status meant. Furthermore, as the system returned to open when they reset the system, they did not realize the changes had been made in the LCS. The load controller received an error message in the system because the number of bags moved by the leading hand meant that the aircraft was out of balance. The load controller attempted to contact the leading hand via the messaging system, but was unaware the leading hand had not subscribed to the system, so the messages were not received. The operator had 2 procedures for load control to notify the leading hand that changes have been made in the LCS. The dead load change ramp tolerance in the standard operating procedures for the flight management mobile application required that load control make a phone call to advise the leading hand or the AMCO that they had denied a change request through the LCS. The second procedure, which is in the controlling document used by load control for out-of-balance operations, required that load control communicated the requirements to the leading hand, which was normally done through the messaging system within the LCS. In this incident, the load controller used the messaging system, which was not effective as the leading hand was not subscribed to the system. Once the loading is completed, it is the leading hand's responsibility to confirm that the LDR reflects how the aircraft has been loaded. Although the leading hand did check, they did not detect the error until after the aircraft had departed. As a result of this occurrence, the aircraft operator issued 2 safety bulletins and updated their system functionality to ensure that only one leading hand can allocate him or herself to an aircraft at a time.
Let's come to a real use case now after seeing the video. we do see that we have a Docker, your backside, right? Docker is a place where a ship is docked and you upload the containers to the ship, right? And depending on the capacity of the ship, it can contain the containers given here. So Docker is nothing but it's got all the cranes, right? So these cranes will do a loading of the containers into your ship. But for this Docker, there is a control which is known as Kubernetes control. So in reality, when we talk of scaling, we have to learn first the limits of scaling when we do a scaling. And we also need to understand what exactly you mean by auto scaling. Auto scaling does not guarantee that your process is stabilized or it's going to run smoothly, right? Can you guarantee here that the containers which have been loaded here from the Docker, people also call it dockyard, you know, can you guarantee that when you load this, the ship is going to be very stable? Not sure, because we saw in the earlier video, here it's a ship is in water and that was your ship. But now let's come to this software world, the real world. And so you see a diagram here where we talk of autoscaling. Where do we see autoscaling here? Yes, we saw a Docker, and you know the Docker has containers, right? Let me compare this with the other one. So what we saw just now was a Docker, which is behind you, right? These are your containers. You're loading these containers, right? So let's have a look at this diagram. And then let's do a comparison. So you have pods here. You have Docker here. I think each pod is just like a ship, right? So what is under my control? Using Kubernetes, I can have a number of pods. And when I can have a number of pods, I can have load distributors also, or load balancers, correct? So now we are connecting the real world with the actual problem. But you need to note this now is that just mere auto scaling here, maybe with Google Cloud or Azure Cloud, is not a complete solution. So where's the complete solution? Okay, let's take for simplicity that this particular Docker is in a software world is nothing but a VMware where you'll open so many pods, right? What is the guarantee that these VMwares are geographically distributed correctly so that the customer will not have a latency? Your auto scaling may not so completely here. So this is one of the episodes which I want to highlight. In the next episode, we are going to learn what exactly is the Docker. How do you make a Docker? That means in the software world, how do I deploy things into Docker? Inside this Docker, I have pods, containers. Inside the container, I will have a Java program or a database. So that's what we are going to see about this in the next episode. But for now, please do give me a comments if you have anything to talk about. But as I know, let's analyze what we did. Is that we took a Docker right? And then so we do have here to summarize that we have a Docker and we have containers, right? So we have something as control. That means from the Docker, the containers are, put into, into the pods, right? Pod 1, pod 2. Not only that, we can have a lot of pods, pod 1, pod 2, pod 3, pod 4. And the Kubernetes is controlling that. So in the next episode, we are going to watch how a software system like Kubernetes is actually implementing that. Yes, we'll do hello world, but we'll go to reality from the hello world. We'll ask some very reasonable and basic questions, which we will see if the existing Kubernetes system can provide us or not. But for now, if you like this video, click a like on this, and this will motivate me to put the next episode on this.